it is time to talk about angles on the hyperbolic plane. If you recall, we defined angles between two curves on the Euclidean plane as being the angle between the corresponding tangent lines. Then we used a similar definition to define angles between two geodesics on a sphere. Namely, when two geodesics intersect at some point, we use the tangent lines to the sphere at that point to define the angle between those geodesics. However, this was possible because we were able to embed the sphere into a three-dimensional Euclidean vector space. So is it possible to embed the hyperbolic plane into some sort of a vector space? Well, before I say anything about that, let's just think about how one generally defines angles in an n-dimensional vector space. So you know that the dot product between two vectors, A and B, is given by the length of A times the length of B times the cosine of the angle between these two vectors. So if I give myself a dot product, then I can read off the angle from that dot product. So there are special types of vector spaces which are vector spaces endowed with a dot product. This dot product, in fancier terminology, in this sort of greater generality, is called an inner product. So we could call them the inner product vector spaces. So Rn is an example of such a space where the inner product of two vectors is just the dot product. So if you have a vector, let's say on the plane x1, y1, and another one x2, y2, you can define the inner product to be the dot product, so it's x1, x2 plus y1, y2. And you can extend this definition to an n-dimensional vector space. So it turns out that the hyperbolic plane can be embedded in a vector space with a somewhat different inner product, where you don't just add all these products of coordinates, you sometimes subtract. Such a vector space is called a Minkowski space. So it is possible to embed the hyperbolic plane in a Minkowski space and without distorting distances, so isometrically embedded into a Minkowski space. And then you can use the definition of an angle to be the angle between two tangent lines, and you can compute angle between lines because you have a notion of an inner product. Okay, all of this is sort of a very theoretical discussion of where the angles on the hyperbolic plane come from. What will be important to us is that when you actually go through all this and descend back down to our hyperbolic plane, that if I draw two geodesics, then the angle between those geodesics, the hyperbolic angle, is actually equal to the Euclidean angle. So it's the angle between the corresponding tangent lines. So just to draw a picture of it, if I have a geodesic like this, so a vertical one, and then another one that's part of a circle, then you might ask, what's the hyperbolic angle between these two geodesics? Well, that's just the Euclidean angle that you get between the tangent lines. So the line to this circle and this vertical line. Similarly with two arced, we call them bowed geodesics. If I want to know what's the angle between them, well, that's just the angle between the corresponding tangent lines. So for our purposes, if you're willing to believe me that this is a sensible way to define angles on the hyperbolic plane, namely for them to be the same as the Euclidean angles, it becomes actually quite feasible to compute angles on the hyperbolic plane. Okay, and to make this even more feasible, we're going to prove the following proposition, or theorem, I guess I call it theorem here. So we have this somewhat complicated picture here. So let me just guide you through this picture. So let P be any point on the hyperbolic plane. So P is our starting point. Then I draw four geodesics through this point. One is going to be the vertical line. So that's gamma. So I denote the point of intersection with the x-axis. So this is the x-axis. To be D. And then there's, I just denote the sort of the point past B on the same line by D prime. And then I draw three more geodesics. One would be gamma 1, so that's a geodesic centered at point C1, so that's the black one. C1 here. The blue one, gamma 2, will be centered at C2. And then there is one gamma 3, which is centered actually then to the right of the point D. Okay, gamma 3. So I kind of would like to study maybe how to compute in a somewhat easy fashion the angles between a vertical geodesic and a bowed one, between two bowed ones that end up, that sort of land on the same side of the point D. So gamma 1 and gamma 2. And then, so I shouldn't say that. So when I want to compute this, I don't want to draw too much of this picture. If I want to compute the angle gamma 1, gamma 2, so that's this angle here. Or if I want to compute the angles of going the other way, gamma 3, gamma 1, so that is this angle over here. And as I said, also this angle, right? So the angle between a vertical geodesic and a bowed one, and then two different angles between two bowed geodesics. So it turns out that it's actually quite easy. So the theorem tells me that if I want to compute the angle between gamma and gamma 1, so that is the angle from the vertical line, I didn't draw it here on the picture, from the vertical one to this one, to the black one, then that's the same as the angle DC1P. DC1P. Okay? So that is this triangle here. Okay, I don't want to draw any more on the picture. DC1P. So the angle between gamma and the black geodesic, which by definition is the same as the angle between gamma and the tangent line. The TI's denote various tangent lines to these geodesics. So the angle between gamma and gamma 1 is the same as the angle between gamma and the tangent line, T1, that's by definition. And I'm claiming that that's the same as DC1P. So the angle in the triangle DC1P. What about gamma 1, gamma 2, the angle between gamma 1 and gamma 2? So this is the one I drew here. By definition, so let's just draw it like this, maybe two of those. So by definition, that is the angle between the corresponding tangent lines. The line to the blue geodesic is this, and the line to the black geodesic is this. So by definition, it's the same as that. And now we're claiming that on the picture, this is the same as the angle C1PC2. So C1PC2. All right, so I just broke my promise. I said I'm not going to draw anything else on the picture. So this is the same angle as that one. All right, and the third one, that's the big one here. From gamma 1 to gamma 3, by definition, that angle is the same as the angle between tangent lines. So this one, between the corresponding tangent lines. And where is it actually in these triangles? That's pi minus C1PC3. So C1PC3, that's this angle, and it's pi minus that. Okay. Let's prove it. The proof is actually not that difficult. But it's a very useful proposition, you'll see. So proof. So first we're going to deal with this angle here. So let D prime, as on the picture, be a point on gamma above P. Above P. All right, so that's just that point over there. So let PT1, PT2, PT3 be tangent lines, be the Euclidean tangent lines to gamma 1, gamma 2, gamma 3 respectively at P. All I'm doing so far is just explaining the picture, right? Introducing the notation in the picture. Okay, So one thing that we know is that tangent lines to circles are perpendicular to the radius that goes through the point of tangency. So as tangent to a circle is perpendicular to the point of tangency, we get that some angles here are right angles, so that's mainly T1 PC1, T2 PC2, T3 PC3. They're all right angles, right? Because let's see, so T1 PC1, T1 PC1, well, C1 to P, that's the radius of this black circle, and the black line is tangent to the circle at point P. So the tangent line forms a right angle with the radius. So T1 PC1 is right angle, and so on. That's the other ones exactly right for the same reason. So what does that give me? All right, so I want to compute the angle between the gamma. Actually, let's do gamma 1, gamma 2 first. So that's the angle, that's the double arc here. So by definition, right, this is just definition. That's the angle between T1 and T2. But that's the same as the angle T1 PT2, right? The angle between T1 and T2 is just the angle T1 TP2. Nothing surprising so far. Okay, so I'm just gonna make the argument here in this corner to keep the picture up there, and the statements as well. Okay, so we're so far. Okay, so this is equal to, so T1 PT2, that's the same as T1 PC1 minus the angle T2 PC1. Right, so this is just like, all right, so T1 PT2, that's the same as T1 PC1, right? So that's this angle minus that one here. So T2 PC1, right? Again, T1 PT2, that little angle is the angle, this one, T1 PC1 minus T2 PC1. Oh, but what do we know about this one? We just said that T1 PC1, which is the same angle as this, is equal to pi halves. All right, so this whole thing continues here. So that gives me that this is pi halves minus the angle T2 PC1. Okay, but what's the angle T2 PC1? So that's pi halves minus, open parentheses, T2 PC1. What is the angle I'm interested in? I would like to get DC1P. So that's actually the angle T2PC2, T2PC2, the angle T2PC2 minus, so T2PC2 minus the angle C1PC2. Okay, again, let's check that. In fact, so the angle T2PC2 is the sum of the angles C1PC2 and C1PT2. So hence we get that. Oh, but this is again, this one is again the right angle. So this is again pi halves. So we're done. So this is the angle C1PC2. Okay, so that proves the first part. let's go on. So I'm going to erase this part now. So now I'm interested in the angle between the vertical geodesic and gamma 1. So let's maybe use this. So now I want to know the angle between gamma and gamma 1, gamma comma gamma 1. So by definition, this is the angle between d prime p t1, right? Because it's the angle between the vertical line and the line tangent to the black geodesic. So it's d prime p t1. Okay, but what is that? That's the same as pi minus the angle t1 pd. T1 pd, right? That angle here that we're interested in is 180 minus T1 pd. All right, so that is equal to pi minus, what is T1 pd? I'm going to write it as a sum of two angles. That's, so T1 pd, right? So that's T1 pc1 plus C1 pd. That's the angle T1 pc1 plus the angle C1 pd. Aha, but this one again, T1 pc1, that's again pi halves. So this gives me pi halves minus the angle C1 pd. Okay. But the angle C1 pd, look, this is a right triangle, so the angle C1 pd is 90 minus PC1d, or DC1p, right? This angle here is 90 minus this angle, DC1p. So this is pi halves minus DC1p. So this is just DC1p. Okay, and this proves the other equality. Let's do the third one now. So I'll erase this. So we're looking now at the angle gamma 3 gamma 1. So that's this angle here, the single arc, which is the same as this gamma. So that's the angle between T1 P T3. By definition, right? That's the angle between these two tangent lines. But this is the same as, okay, now I'm going to sort of go around. That's 2 pi minus the angle, is it going to be sum of angles here? So it's T1 PT3. I'm just going to go sort of around this circle. So it's 2 pi minus that other angle. So that's T3 PC3. I'm doing it because I know T3 PC3 is actually 90 degrees. Okay, so it's T3 PC3. Then I'm going to do C3 to C1, so plus the angle C3 PC1, and plus, so finally C1 PT1. C1 PT1. All right, but again, there are two right angles here. So this is right by this, right? And then there is also that one. That's also right. Pi halves. So if you do this, so I have 2 pi minus pi halves, so I only have pi left. So that's pi minus the angle C1 PC3. I just reversed these two, and this is exactly what we wanted. Okay, so this finishes the proof of it. In the next part, we'll see how to use this to in some practical situations.